Hello, everyone. My name is Sid Hussmann. I'm the CTO and co-founder of Gapfruit. So, 3 years ago, the infamous Professor Timothy Roscoe gave a keynote at the Usenext conference where he ranted about the lack of innovation in systems engineering. Well, times are changing. On the one hand, we have new app runtimes, such as the ones for WebAssembly. Then we have the whole industry pushing forward zero trust principles with public key infrastructures and hardware root of trust. Then we have the communities such as the ones around Genode, Cubes, or SEL4 that push the possibilities when it comes to secure systems design. In my talk, I want to combine these positive movements in one integrated product. But first, who in this room has worked with capability-based security? All right. Just a short overview of where we come from. My team started developing real-world products with microkernels and capability-based security for over a decade. In early 2018, I co-founded Gapfruit with the aim to bring this technology to the business market and the industry. We now run on HSMs in the banking industry, and in 2020, we developed with Securasys a trusted execution environment for transactional workloads in the finance industry. This is the first time we implemented a WASI runtime in a product. This product lets you prove that a certain code has been executed at a certain time with specific input, specific output, and it provided a proof of the trusted computing base at that time. Since 2022, we target the industrial IoT sector with partners such as Bechtle, Device Insight, or Coded. So to make our OS tangible, I'm going to talk about connecting industrial equipment securely to the cloud and at scale. So this requires a holistic convergence between the OT world and the IT world with rock-solid security. So also, we may want to process some data near that equipment for latency reasons. Then this gateway acts as a first line of defense towards untrusted networks, such as the evil internet. So we have to guarantee the availability, the integrity, and the confidentiality of that industrial equipment in that order. So industrial equipment needs to produce always. Otherwise, it gets very expensive. Traditionally, these devices have been a pain to set up, a pain to write applications for, a pain to maintain, and an absolute nightmare to keep them reasonably secure. Let's change that. So here we see an industrial solution where WebAssembly already plays a role. Obviously, on the left in the browser of the operator. Then the cloud natives were like, this is neat. Containers have become so bloated. What if we could use WebAssembly instead? This is where WASI comes into play. It follows a capability model where you have to explicitly grant access of resources of the service of the underlying system. Now, with Docker announcing the support for Wasm Edge, what we get is a way to develop and package software like we're used to, but not for containers, but for WebAssembly. Additionally, these apps are only a few megabytes in size and spin up very, very fast. So this movement on the application layer is great news for us systems engineers. We can now run the same unmodified apps from the cloud folks on our awesome new operating systems. So what are the ways to develop a WebAssembly app to run on Gapfruit OS? So Goa is a tool that targets application developers to build, test, and publish software with different runtimes and programming languages. What we see here is the structure to package an unmodified example from Wasm Edge, which is a simple Rust server. The archives file here states the software bill of material. This means like the direct dependencies such as Wasm Edge, but also the transient dependencies such as LLVM, spdlog, the POSIX shim, or even libc. And the runtime file states the internal component topology of that subsystem. I will go into service topologies later in my talk. So in this short demo, I will adapt the Rust example to make sure what I'm going to run in the future is the one that I'm compiling now. So we see the same structure, adapting the version file to today, and then I'm changing the Rust server. More specifically, I'm changing the handle HTTP function, and I'm printing out, I'm going to echo this on the edge one day with whatever I received over HTTP. Now I'm going to do a Goa run, which compiles the app and runs it within a Linux environment that is isolated also with seccomp, but that's beside the point. And here I can do this curl request. I'm going to echo this on the edge one day. Computer says hello. All right, now I'm going to package everything, which means Goa publish, which means creating tarballs and sign them with my development key. And then I'm going to upload this to a remote server to be pulled at the later state. Let's come back to our gateway example. What I want to talk about next is two claims or two major benefits of Gapfruit OS for the industrial IoT. So one is we reduce the attack surface by way over 99%. The other is how we handle mass IoT deployments. So we take some security concept and we leverage it for mass deployments. But first, just a little overview of Gapfruit OS. So Gapfruit OS is a microkernel operating system with capability-based security. We built the operating system with a Genode framework, and from a technical perspective, there's some things to point out. Like the Genode framework enables you to design custom systems with different microkernels. What they also provide is this Linux device driver environment, which is an absolute game changer, because this enables us to benefit from the vast Linux ecosystem when it comes to hardware support. This also provide different migration paths, and Genode has this nested system configuration mechanism that lets you launch a dynamic subsystem from a static one. And we extend this mechanism with management agents, such as the one with the telco standard TR369. And then also we implemented an Azure agent with our friends at Device Insight. Let's come back to my claim of reducing the attack surface by over 99%. The design that typical operating systems have is way over half a century old. So and it's simple. We have hardware, we kind of abstract the hardware with a kernel, and then from the application layer, we use this abstraction with system calls. So from a software perspective, the kernel is the most critical part of the system. From the application's perspective, the attack surface to the kernel is huge with over 300 system calls. So there are ways to mitigate this, right? There is seccomp and stuff like that. But this is actually where WASI plays a major role, because with WASI, you explicitly grant the access to the system, which limits the attack surface significantly. However, I want to emphasize a little bit more on the underlying kernel. So the design makes it in a way that everything in a kernel is critical, right? And with 36 millions of lines of code, every line is critical, and every line you need to trust. So if you exploit a likely bug in something inherently complex, such as a network driver, it's basically game over. And each of these hundreds of drivers have that huge attack surface. So how does that same vulnerable Linux driver behave on a Gapfruit OS with the Linux device driver environment? Well, every component is strongly isolated and only has access to resources they really need. So a connection from a management agent to its cloud counterpart, the integrity and the confidentiality stays intact even though this driver may be compromised. So we push the trust outside to the already untrusted network. When it comes to availability, our resilience system will detect a misbehaving component and just restart this without any impact of the rest of the system. So how does that look like? On the left, you see the serial output of the gateway, of the physical gateway that I have in my hand. Here. On the right, I'm starting an SSH client to connect to that gateway. I can start Vim. I have a little minimal bash environment, but that's beside the point. I want to showcase that I keep being connected even though I restart the driver because it page faults. So I'm going to attack the driver, and at the 10th ping there is a page fault, and I'm pressing enter, and you see that little glitch, right? Oh, here I am again. And I'm still connected, right? And here I can see, all right, there is a page fault. I'm just restarting the driver. And that whole system is running as usual. And even the connection between the SSH connection, there was no impact to it. So what happens with that same vulnerable driver on that regular CompuLab board support package with a standard Linux interface? So I'm logging in. So this is a IMX8 SoC, by the way. Right? I can do a uname. I can barely see it. Huh? So I'm starting the attack on the right. Uname, so this is the Linux version. What happens with a page fault? Kernel panic. So for the Windows folks in here, this means like blue screen. So imagine happening that on your fleet of devices right now. So you have to act, right? Now I'm going to talk about my final topic, which is TPMs. Here's a list of stuff that we use TPMs for. For those of you who don't know about TPMs, TPMs are like this hardware root of trust with a standardized cryptographic interface. What I want to emphasize, however, how we use TPMs for authentication. So we leverage a security concept to enable mass scaling. This slide shows the physical provisioning of this gateway at the factory. The CA creates a new root certificate for a specific customer or a specific cluster. And on Azure DPS, we create a new enrollment group and define that initial desired state that my fleet of devices should have. And I'm going to import this root certificate to that enrollment group. This means that any device coming with an intermediate certificate is being granted access. On the device side, more precisely on the TPM, we create a new public-private key pair, and we issue a certificate sign request to the CA, and we prove that this key has been generated by a TPM and that it's non-exportable. So this private key will never leave that discrete hardware. On the top, we have a credential manager that creates short-lived certificates for management agents such as the Azure agent, but also for applications that may require some form of authentication towards the cloud. Now I come to the real demo that combines everything I've talked about so far. So the end goal is to deploy the Wasm Edge app that I built on my x86 Linux machine to this ARM device by only powering up. Before starting the demo, here the few steps. So the gateway is installed at the factory by the robot. It's being powered up. The LTE driver is starting. The first thing that the management agent does is to connect to the Azure DPS. DPS will then create a device twin and load that initial desired state to that device twin. And the management agent will then know, all right, this is the desired state. So there are some software that I need to pull and hint the package that I deployed before. And then once everything is installed, we can spawn that Wasm Edge app, and the robot is able to connect to that app. All right, let's see how this looks like. So on the left, we have the OT world with the gateway at the bottom and the robot on top. On the right, we have the Azure world, where I issue standard Azure CLI commands. And here I'm going to specify the initial desired state, which runs the Wasm server with that specific version. I'm going to now set the desired state, and this gives me some output. So the attestation mechanism is the root certificate that I talked about, and then the initial desired state is whatever I've showed before with that Wasm server and the exact version that I deployed. On the top, I'm now connecting to the Azure IoT Hub to the specific device twin. Well, this will obviously fail because the device has not booted yet, so there is no device twin. So I'm going to continue checking for the reported state of the device twin until I succeed. On the left here, the robot is trying to connect to the server, which will obviously also fail because the app hasn't been deployed yet. So I'm also trying to do that until I succeed. On the bottom, we see that the gateway is booting. We see LTE coming up. We see the short-lived certificate being generated. And we see the management agent connecting to the DPS. All right, this goes fast. And the IoT hub. And then we see that stuff is being pulled, such as Wasm Edge, SPD lock, POSIX, shim, OpenSSL, and stuff like that. It's now being verified for the integrity and extracted, and now this Wasm Edge server is running and listening on connection 80. and the robot is able to connect. I'm going to echo this on the edge one day. Robot says hello. On the right, I can browse through the reported state of the device. But what I want to emphasize is that what I showed you by powering on one device obviously scales to tens of thousands of devices. So I learned that it's always better to have something tangible before talking about concepts. But now you get the basic feel, right? So let's talk about concepts. So there are three main concepts of Gapfruit OS. So first, everything runs in user space. And we have strong isolation guarantees by the microkernel. This means that every component in a system is strongly isolated and only has access to resources they really need. This is done with a capability-based security. So there are three types of dependencies in a Gapfruit system. The first type is about the software bill of material. When people in software engineering talk about dependencies, they often mean some form of library dependency. So especially from a security perspective, but also from a maintenance perspective, you need to be careful which libraries your apps depend on. Our package management system is inspired by Nix, so you always know the exact dependency graph during build, during deployment, and during runtime. The second type of dependency is about how components interact with each other, or subsystems. So in Genode, this is done with a service-oriented architecture where a client depends on a server. So this might need an example. So one that we've already seen so far. So service-oriented architecture lets you abstract the hardware. Like the network driver is using I/O memory session and interrupt session and transforms it to a higher level network session. What you can also do with a service-oriented architecture is that you can design a very resilient system. You can now design a system where you design it in a way that the complexity is being handled by not having other components depend on it. So this network driver is a pure client in this case. What you can also do is identify the actual critical components if they are like a server, or especially if they are multiplexers that have an impact on security. So you now can identify these critical components and you can work on the quality, right? You can now do stuff such as limiting complexity or doing rigorous testing, or even go down this route of doing formal verification. So the last dependency type is about how resources are distributed. This is about this is done with a parent-child relationship, where the parent provides resources such as RAM, CPU time, and capabilities to its children. So the parent controls basically the connections of the service topology of its children. In other words, the parent controls the capabilities of all its children. So what we see here are three views of the same system, and you're probably wondering, why the hell is he telling me all this? Well, with strong isolation and control over all dependencies, you can now argue about the trusted computing base of each component, subsystem, or even driver inside that product. Let's explore some systems where these principles can be useful. So there is a discrepancy between safety-critical systems and security-critical systems. For one, the safety-critical systems mean that the system must not harm the world, and security means that the world must not be able to harm the system, right? When it comes to engineering practices, they also kind of differ. For the safety-critical products, it's required often required for the certification bodies to follow a rigorous process, like requirements engineering, specification, and then implementation, testing, validation. And then once you have finished your product, and you have to certify this. And this certification is very, very expensive. And this provides like this weird incentive to never ever touch your system again, because that recertification is so damn expensive. So, however, if there is security involved, let's say if there is a vulnerability in OpenSSL, you need to act fast, very fast. And so you see the clash, right? What those two folks agree on is that low complexity usually means better quality. In safety critical systems, it means better safety, but it also means less certification cost. So there is a number from the automotive industry that states that every line of code costs $80 to certify. So this, you might want to not write everything in one line, guys. But yeah, but in security, it's also low complexity means less bugs, and less bugs means less exploits and better security. So let's come back to this this slide. So with strong isolation and capabilities all the way down, you can now design a safety critical product and certify the green stuff without having to recertify that product, or with minimal recertification if you update like a security critical component, like updating OpenSSL. For the other, you can identify the critical parts and make them as strong as possible. So this will all help for certification, such as the European Cyber Resilience Act that everyone is afraid of. So what are the use cases for capabilities all the way down? Well, products on the verge between OT and IT, which are in use for decades. And then products on the verge between safety and security, and basically any product where security matters. Thank you. Any questions?
WebAssembly is okay. Okay, WebAssembly came in a bit late in the system after a few years of working without WebAssembly. So, what was improvement before and after WebAssembly in security and safety?
Yeah, Dan just showed a very good slide, upstairs. It's Steve Ballmer screaming, developers, developers, developers. Because it's literally, for us as an OS vendor, you don't want to go through the pain of porting every software that has been built. And so I'm looking into this room, and I hope you guys will do that for WebAssembly. Yeah.
Thank you. Hi, great talk. What are the current use cases that you like already have with, I don't know, customers, for examples, and can you also disclose some companies maybe? And also the other thing with like the certification of a code line, I think if you put everything in one line, it will not be 80 euros anymore or dollars. It will be,
of course. Yeah.
It will scale up as well.
Yeah, of course. We have. So we're in the banking industry, but that is another niche. So we're now focusing more on industrial IoT. So, and we have made like 10 proof of concepts, and we are now right on the verge of going into the market. Yeah. And our partners are Bechtle. I don't know if you know that. It's one of the largest system integrators in Europe.
Maybe also already in discussion with car manufacturers?
I can't disclose that.
I see. I work for Mercedes-Benz, by the way.
Oh, okay, we should talk. All right. Any other questions? All right. Thank you.